Welcome to the next lecture of Software Design and Modelling. So today we're going to talk about language engineering and domain-specific languages. I'm going to go over how we define languages, especially modelling languages to start with. Then we're going to have a bit of a general talk about general-purpose languages versus domain-specific languages and why you might ever want to use a domain-specific language. And we'll talk about various technical features such as the difference between internal and external domain-specific languages. We'll have a bit to say about the significance of modelling in this context, and we'll briefly mention some technologies. The remaining labs, although exactly what they are varies from year to year, will have some relevant examples in them. People sometimes think they can skip the labs after they've done the lab assessment, but you please must do the labs. They are important and will help you understand some stuff which is quite difficult to grasp if you only see very brief notes on slides about it from a theoretical perspective. So, let's quickly revisit some of the ideas that we've already seen in the context of how we define UML, which is a general-purpose modelling language, but now we're going to look at the same technical material from a slightly different perspective because we're going to be thinking about our new task of defining a domain-specific language. So, recall, languages have syntax, semantics, and pragmatics. And the syntax is one of the things that the language designer has to define. And for modelling languages at least, we can split syntax into two different concepts. We can talk about abstract syntax, and that, if you like, is the information that's needed in order to determine the semantics. It's the stuff you need to know about a model in order to know what that model means. So it covers things like what elements are there and how are they related. And then we also have concrete syntax, which is what does the user actually say? So what are the keywords if you're talking about a textual language? What are the shapes of the graphic elements? So, for example, abstract syntax says things like there are going to be classes and associations between them, and concrete syntax says things like classes will be represented by rectangles and associations by plain lines. And syntax helps us to answer questions like what expressions are there in this language, and is this particular expression legal in the language? That's what you can do with syntax. Then the other thing the language designer has to do is to define semantics in some sense, and all we mean by that is, given a legal expression in the language, what does it mean? And in the case of modelling language, the way that typically is easiest to think about is to say, if I give you a model and I give you a system, you should be able to answer the question, does the system conform to the model? And one way of thinking about that is via denotational semantics. We're going to say, given a model, there's a set of things that this model could mean, could be referring to, a set of things that conform to this model. And then the question we want to be able to answer is this system one of them? Pragmatics, on the other hand, we mentioned those before with layout of diagrams as the classic example, and these are emergent. They are almost by definition not things that the language designer sets. They are things that users determine by how they actually use the language in the end. So they're conventions of use that emerge. But why are we even talking about defining languages as a thing we might need to do in the first place? Isn't it enough to say, we've got UML, it's a standard language, we talked about the advantages of there being a standard language, why would we need any more? Well, an exactly similar question is, why is there more than one programming language? Now, if this weren't a video, we would now have a class discussion about it, and we may yet in a live session, but I just invite you now to pause the video and have a think for yourself. Why is there more than one programming language in the world? Are you back? Well, hopefully you thought about a bunch of different issues relating to how some tasks are easier to complete in one language than in another, and how we might want different properties of solutions to different problems, such as different kinds of verifiability, such as different performance characteristics, and so on. Coming back to our position as users of languages, including modelling languages, let's think about what we might do apart from defining a language. So what actually are our options if we land ourselves with a problem? We find that our domain is somehow difficult to work with. I haven't quite said whether we're talking here about programming languages or modelling languages, and for the sake of argument, let's just say here that we could also be saying textual languages or graphical languages, although, as we shall see, it's not really the case that it's a programming language, if and only if it's textual. What is the difference between programming languages and modelling languages anyway? I think this comes up on a later slide, but the key thing I think is that programming language is in some sense giving you complete information about what you want to happen, whereas a modelling language is deliberately not doing so. So even though this distinction blurs if you start pushing it, because the programming language doesn't tell you everything you need to know about what the computer will do, you tend to think about a program as though it did. Okay, you think about programming as being tell the computer exactly what you want it to do, whereas modelling is kind of explicitly saying I know some things about what I want the computer to do, but not others, and so a model is deliberately abstracting away from some information that's not specified in the model, but maybe might be specified in some other model or decided at some later time. Typically in the programming language, the way you think about it is the stuff you're not specifying in the program is usually stuff that you don't care about very much. You're very happy to have that decided by the compiler writer. But this is not an absolute distinction, as we shall see. So, imagine that you're in overall charge of your organization's software and you're finding that you have a problem building software to work in the domain where your organization is active. Things are not easy enough, it's taking too long, the software is too expensive to develop. What could you do? Well, you could just, do nothing special. You could say, well, my favourite programming language is Turing Complete. I can program absolutely anything in it. If things are not going fast enough, well, I don't know, maybe we need to employ better programmers or something. That's a possibility. Sometimes it's the right one. And by the way, of course, there are lots of things you can do about problems of development other than change the technology. You might want to look at your development process, you might want to look at your team structure, all kinds of things. I quite flippantly said maybe you need some better programmers, but maybe you need a better environment for programming. That could well be the case. Or maybe you can get better software reuse. Maybe there are some classes that it would make sense to write once because they represent recurrent features of your domain, and reuse them from system to system, and maybe that might save you a lot of effort. Maybe you might even develop a library of them, a class library, and say every piece of software developed in my organization is going to use this standard class library, which we can then make sure is highly tested and well adapted to the domain, and perhaps that will save us a lot of effort. A subtly different thing you could do is to develop a framework. And we've not talked much about frameworks in this course, although we could have done. What's the difference between a framework and a class library? Typically the difference is that a framework constrains the overall logic of your application in a way that a class library doesn't. So a framework will very often use what's sometimes called the Hollywood principle. Don't call us, we'll call you. You might, for example, find that you have a framework for, a data entry application, where the logic is all laid out in the framework, and in order to use the framework, what you have to do is to write certain classes or methods to slot into the framework at predetermined places. So more of the work is done for you, typically in a framework, which means that you may have an easier job using it, and it also means that you may have less flexibility. So there are pros and cons. Slightly different angle, we talked earlier about fluent interfaces. You might want to make sure that your APIs, that the interfaces to your classes, for example, provide a fluent interface so that people who are writing applications in terms of them have an easier time writing code which is quite readable and quite easy to construct, making use of those features. Or you might want to develop a domain-specific language, and you can see a domain-specific language as being the next step after a fluent interface. We mentioned, I think, when we talked about fluent interfaces that this was kind of a stepping stone on the way to having something that really would feel like a specific language. So what's the difference between a domain-specific language and a general-purpose language? Well, there's no precise cut-off point, no precise definition of what it is to be a DSL. I quite like this table which I've taken from a nice book by Marcus Volter, which is freely available at that URL, and it's something you might like to look at if you're interested in the area, and I'm going to have a reference to that and some other things at the end of the slide set. But basically speaking, DSLs pick more characteristics from the third column than from the second column. So we're looking at things like, a domain-specific language is going to be typically a small language, and that means it can be quite well defined. So because there isn't too much to define, there aren't too many features. Okay, and that in turn has effects such as it's relatively easy to support them by tools. Whereas as we've seen, GPLs like UML can easily end up being large and complex. A DSL might not even be Turing complete. It might not provide things like sophisticated user-defined abstractions in a way that a GPL is quite likely to be required to do. We'll say something about execution in a moment. And a DSL can move quite fast because it's controlled by a relatively small number of people, and it has a local user community. It's either people who work in a specific application domain, possibly even people who work within one organisation or even part of one organisation, and that means it's possible to evolve a DSL, to change it, and to make even changes that aren't backwards compatible in a way that's very hard to do with a general purpose language that lots of people in different areas are relying on possibly in different ways. So a DSL tends to be sort of smaller and more agile. So let's just check that you understand this, and again, in a non-video situation I would probably do this by show of hands in a classroom, but you'll have to imagine that part. Which of these things are DSLs and which are GPLs? Start off with some easy ones. Java is a GPL. Haskell is a GPL. UML is a GPL. It's a GML really, isn't it? A general purpose modelling language. SQL. Now we're getting slightly dodgy. This, I think, it's fair to say, is a domain-specific language. Okay, it's a language which is specific to the domain of defining queries. HTML, again, probably a DSL. Makefile, a DSL, helps you to define the dependencies between modules in a system and how a system should be built. Use case diagrams. Now, we said UML was a general purpose language. What about use case diagrams? Here we're starting to get a little bit on the fence. Most people would say use case diagrams were a domain specific language, I think. And you're starting to see that we might say, well, if you have a collection of related domain specific languages, maybe you start to have an argument for saying, well, between them they make up a general purpose language. But these things aren't very important. You can tie yourself in knots over them. What about scientific notation for numbers? I think we usually say this is a domain-specific language. It's a language, very simple language in this case, specific to defining numbers. So there's not an absolute binary distinction between DSLs and GPLs. We can ask, well, how general purpose does it have to be, or specific to what domain? If your domain gets big enough, then you're in the land of general purpose languages. Somebody might argue, for example, that UML was a domain-specific language because it's specific to the domain of wanting to model object-oriented systems. Well, most people would say that domain is so big that it's general, but you don't have to worry about the fact that there are grey areas. Sometimes the distinction is useful in practice. Now, there are two main kinds of DSL, and it's useful to understand this distinction because it has quite a lot of effects on what it feels like to use a DSL and of course what it is like to define a DSL. So there are internal and external DSLs. So an internal DSL has text which occurs inside a program which is written in a host language, a host GPL, and it gets parsed along with the general purpose language instance itself. So you don't have to write a parser, you're using the parser of the GPL. and it's convenient for programmers who already know the host GPL. It just makes something or other easier for them to do than it would be otherwise. And an example, and I think I specified some reading on this, is SQL queries embedded in Java programs in particular ways that support the writing of SQL queries. On the other hand, if you have an external DSL, then we're talking about programs which are freestanding. They have their own parsers and so on. And because they don't have all the complications of a general purpose language surrounding them, they can be more friendly to non-programmers. And a classic example would be a makefile. Returning to the high level of the pros and cons of developing a DSL, any DSL, here are what I think are the key ones, though you may well be able to think of others. The main advantages of developing a DSL are that you can give it exactly the features that you want it to have and none other. Okay, so you can keep the language as simple as it can possibly be while allowing you to express what you want to express, and that means that you can make it nice and concise and highly usable, and efficient to use and efficient to verify and so on. The arguments against are your users have to learn it, and that's never free. Even if your language is, it's easier if your language is more concise and usable, but it's never completely free. You have to develop it, or rather somebody has to develop it. And the hard part is not the development of the language in the first place, the hard part is the maintenance associated with it. So we gave as a characteristic of DSLs that they are able to be changed because they have a relatively small user base, but that of course has costs, because now you've got programs in your DSL. You've probably now got programs in version 1 of your DSL. Now you've moved on to version 3 of your DSL. Well, can your version 3 parser still parse programs that are written in version 1 of the DSL? Do all the surrounding tools still work with it? Do your engineers understand the differences between the various versions of the DSL? And so on. And also worth mentioning is that often the technology that you use for defining the DSL and its associated tools can itself be stuff which is quite experimental these days and can be quite flaky, and you may have to worry about maintenance of that, versions of that, keeping your languages in sync with the changing capabilities of that platform, whichever one it is you use. And that can quite easily land you in a situation where you have kind of business critical software standing on top of quite a shaky edifice of underlying technology, and so you have it's a thing to be approached with some caution, developing a DSL. Nevertheless, as some of the reading will show you, there are organizations that do this with a great deal of success. How does a DSL program actually do something? Fundamentally, there are two ways of doing it. Either there has to be some engine of some kind, some other program, that directly takes the DSL program and does something as a result. Or else there's some kind of compilation or code generation stage where there's a translation that happens from the DSL program to something else for which we already have a mechanism to make it do something. So you might, for example, say, here's my DSL, and what I do is I run this translator that translates my DSL program into Java, and then we use it just like any other Java program as though it had been written in Java. And that's probably the commoner way of using DSLs, actually. So we said that in the modelling world, at least, you need to have both abstract and concrete syntax. Which do you actually write first? Well, remember that in the paleo example right at the beginning of the course, what we actually did was we started off with an example, just one example in our case, not even a family of examples, in a candidate concrete syntax. And then we worked out an abstract syntax, and on the basis of that we thought about, well, what other concrete syntax programs could there be, and do we understand them, and do they express the kinds of things we want to be able to express? And that worked quite well, and that's often a good way to do things. So we used the concrete syntax examples to elucidate the abstract concepts. The downside is that if you're not careful, you end up stuck with oddities in the concrete syntax, which you don't really quite realise are oddities until you've thought about the abstract syntax. And so it's probably quite a good idea to be then reflecting on the concrete syntax and improving it in the light of your new understanding. But you can start at either side. So one thing you might like to do is you might like to first start off by writing the abstract syntax. So you say, well, what are the concepts we're trying to express here, and get a really good understanding of them and their relationships, and then think, well, what is the right way to express this in concrete syntax? What do we mean by the right way? Well, we're largely talking about usability here, because we probably are kind of fixing ultimately the expressiveness. We're saying we have a fixed idea of what we want to be able to say in our language, and the key question here is, how do we want to be able to say it? And so that's really about how usable is our language. Of course, really, language usability does involve semantics as well as syntax, and it's a fascinating area, and I don't have time to say any more about it, so I won't. And what do we do about defining the semantics? Well, I mean, in practice, if you're defining a language, you don't do it with no idea at all of what the semantics is, because there's a reason why you were defining the syntax and why you were defining it this way, so you had some rough idea of what the semantics was. How do you actually go about making that precise? Well, that's really quite hard, and it's different depending on whether you're talking about a programming language or a modelling language. So for a programming language, although there are programming languages that have formally defined semantics, usually what the semantics of a programming language is in practice is, well, what does the reference compiler do? And there's a whole bunch of different ways in which you can define semantics properly, formally. You can use operational semantics, which is about how expressions reduce to other expressions, or denotationally, which is about mapping expressions in the language to some well-understood domain, or axiomatically in terms of what follows from what. Modelling languages, where, as we said, we are constraining what the system can do but not defining it completely, doesn't really have the same range of options for formal semantics. One really wants to be taking a denotational view, as I indicated before. The key question is, if I give you a model and a system which claims to be implementing the model, does the system in fact conform to the model or not? That's the question that you need to be able to answer somehow. And although there's a vast amount of academic work on formal semantics of modelling languages, not much of it has really entered use. So in practice, there may be a code generator for generating some aspects of the code, and that's probably about as close as you get to formal semantics. But of course, it is very important to have a precise, informal understanding of what the semantics of your language is, and that is easier the simpler the language is.